write to a function f of x, let's take the drawing of f of x and then use that information to draw out sketches of f prime of x and f double prime of x. So what do we look at when we're doing this? Well, first let's find critical point. So critical point, critical point, critical point, horizontal tangent line. So that means that at least critical points, the derivative has to be 0. Now, in between these two critical points, our function is increasing, which means that the derivative, it has to be positive. Between these 2 points, the function is decreasing, so the derivative has to be negative between those 2 points. Over here, our function is increasing, so the derivative is positive. Over here, the function is decreasing, so the derivative is negative. Now, we can sketch out f double prime of x by doing the exact same thing. So critical point of f prime of x is there. So we know f double prime of x has to be 0. Critical point of f prime of x is there. So same point, f double prime of x has to be 0. And so between the two critical points of f prime of x, our f prime of x is decreasing. So f double prime of x needs to be negative. F single prime of x over here is positive. So f double prime of x needs to, over here, f prime of x is increasing. So f double prime of x needs to be positive. Over here, f prime of x is also increasing. So f double prime of x needs to be positive over here. So this is a good exercise. Do practice out doing all of these sketches. We should be comfortable doing this. But let's see what else we can get here. So a couple of things that we can get is that we can see our inflection points here. So we see we have 2 inflection points. Let's chase them all the way up. So a couple things here. From the graph of f of x, we can see, yeah, this inflection point, a function is concave up over here. It's concave down. Then it's concave up. So those 2 green points, we can see that's when the function's changing concavity. And that's corresponding to f double prime of x is equal to 0. But moreover, note that this is exactly where f prime of x has the local max and local mins. So inflection points of f, that's equivalent to f prime of x has a local max or min. But there's even more that we can get. Let's think about what's going on at the critical points, not at f prime, which you already talked about, but f itself. So here we have a local minimum, and we can see at our local minimum, our function is concave down. We can see that f double prime of x is positive over here. But if you think about, yeah, local minimum are going to occur when our function is concave down. A local maximum like this is going to occur when our function is, sorry, I'm getting this backwards. This is when our function is concave up is a local minimum. Function is concave down here is a local maximum. It's easy to kind of get those confused. You think down, oh, that's a negative thing. That should be a minimum. Well, no, concave up is a local minimum. Concave down is a local maximum. So putting all these pieces together, so recall this first derivative test for our critical points. We found critical points, how to identify as a local max or local min. Well, we now have a second derivative test. So we have a critical point. Let's say you take the derivative set equals 0, figure out that the derivative doesn't exist at a point to identify a critical point. Well, all we have to do is check the second derivative at that point. If it's positive, that point's a local min. If it's negative, it's a local maximum. Should point out it's also possible for the second derivative to equal 0. In that case, our second derivative test is inconclusive. It might be a local min, it might be a local max, or it might be neither a local max nor a local min. We know that some critical points are neither local maxes or local mins. So this is a second derivative test. In the next video, we'll do an example or two using the second derivative test.